they called it impossible, to make a brain out of water. In 1936, deep inside the Soviet Union, an engineer named Vladimir Lukyanov watched concrete crack as it dried on a building site. No chart or formula could predict it. He wondered, what if nature itself could show the answer? He set up a network of glass tubes, valves and tanks. Into it he poured coloured water. As the water rose and fell, patterns appeared. The same curves the mathematicians struggled to draw. The flow was the calculation. What he built became the first hydraulic analog computer, a machine that used pressure and flow to solve differential equations. The world would later call it the Water Integrator, or simply the brain made of water. When the Second World War began, engineers everywhere faced a new kind of problem: explosions, shock waves, and heat. Equations multiplied faster than slide rules could follow. While others turned to electricity, Lukyanov's team turned again to water and proved that sometimes the simplest element could think like a machine. Before electronics, engineers saw that fluids and electricity obeyed the same laws: pressure and voltage, flow and current, resistance and friction. Each pair mirrored the other. The idea wasn't mystical, it was mathematical. The equations that governed circuits and the equations that governed water flow were identical in form. That made water the perfect medium for a living diagram. Lukyanov formalized the concept. He connected chambers with pipes, inserted calibrated orifices, and mounted glass gauges so the levels could be read as numbers. Each chamber stood for a variable, each valve for a constant, each junction for an operator. When he opened the main inlet, the system began to solve itself. Instead of numbers written by hand, the levels of water were the answer. Where mathematicians struggled for days to integrate coupled heat and diffusion equations, the Water Integrator reached equilibrium in minutes. Early prototypes in 1936 filled a single bench. By 1939, Lukyanov's workshop produced machines that occupied entire rooms. They could handle two-dimensional and three-dimensional problems, the kind needed for concrete curing, soil cooling, and later shock and blast propagation. In these machines, time wasn't simulated, it flowed. Each second of physical time corresponded to a step in the equation's progression. To change a coefficient, an engineer twisted a valve. To reset, he drained the tanks and began again. The accuracy astonished Soviet physicists. Experiments that once relied on empirical tables could now be modelled directly. In 1939, the Moscow Energy Institute adopted the method. Soon the Academy of Sciences requested units for hydrology and thermodynamics. When war broke out, Lukyanov's invention had already become an industrial tool. What he couldn't know was that it would soon serve as a model for wartime analog computing everywhere, not by design, but by philosophy. Where others built with copper, he built with water. Where others used electricity, he trusted gravity. And when steel was rationed and circuits scarce, his materials were things any factory could spare. The genius of the Water Integrator was not its complexity, but its simplicity. It turned the physical world into mathematics, and mathematics back into the physical world. In wartime, that idea, that reality itself could compute, would prove priceless. By 1940, war had become a contest of physics, not just guns and armour, but the invisible mathematics that governed them. The shape of a bomb casing, the strength of a bunker wall, the range of a blast wave, all depended on equations too complex to solve by hand. Slide rules and logarithm tables, once the tools of industry, now looked like toys beside the magnitude of the problems. Each explosion was an experiment in chaos. How does pressure move through air? How do waves reflect off buildings? How fast does heat soak into steel? Every answer required solving non-linear differential equations, the hardest kind known. In Britain, the Admiralty Computing Service tried to manage the load with mechanical calculators and human computers, entire rooms of clerks. In America, the National Defense Research Committee built electromechanical differential analyzers, great whirring machines of shafts, gears, and disks that could plot a function across paper. And in the Soviet Union, under siege and scarcity, Lukyanov's engineers turned again to the medium they had in abundance, water. They realized that the flow of liquid through a network could reproduce the same partial differential equations that defined heat, pressure, and stress. To the outside world, it looked like plumbing. But to the engineers who stood beside it, valves hissing, gauges trembling, it was mathematics made visible. The Water Integrator became a silent participant in the Soviet war effort. Official records remain sparse. The war's secrecy and chaos buried many archives. But post-war Soviet publications confirm that Lukyanov's system was used to model heat diffusion in concrete bunkers and soil stability around fortifications, vital in the defense of industrial cities like Moscow and Magnitogorsk. It wasn't the only analog path. In Germany, hydraulic control systems drove anti-aircraft predictors. In Britain, fire control computers combined hydraulic servos with mechanical integrators to aim naval guns. Everywhere the problem was the same: turn equations into motion, let the machine think through the problem faster than a human mind could. The war turned engineering into strategy. Every design meeting, every laboratory test became a battle in miniature. And behind it all stood the same principle Lukyanov had discovered before the war. If you could represent the physics of the world, even crudely, in a physical medium, then you could understand it. In the Soviet Union, Lukyanov's students refined his creation under impossible conditions. Glass was scarce, so they built chambers from tin and steel. Water pumps were unreliable, so they used gravity-fed systems from elevated tanks. The equations they solved were written in chalk on blackboards, smudged by candlelight when the power failed. One report from 1943 describes engineers at a frozen site outside Moscow, their integrator half buried in snow, still running calculations for heat loss in bunkers. They poured hot water into the tanks to keep it from freezing. It was the image of Soviet science itself, battered, cold, under attack, but unbroken. Even as Allied laboratories developed electronic analog computers, precursors to the first digital machines, Lukyanov's hydraulic computers endured because they needed nothing the war could take away. No vacuum tubes, no copper wire, just ingenuity and persistence. The method spread beyond physics. By the war's end, hydraulic analogues were being used in civil engineering, hydrology, and thermodynamics. In 1944, as the Red Army advanced westward, teams of Soviet engineers carried portable water integrators to model bridge stresses and river crossings. They could set up the apparatus in a field tent, run a calculation, and decide whether a temporary bridge could bear a tank column. In those moments, mathematics was not an abstraction, it was survival. If the water integrator had stayed a laboratory curiosity, it might have been forgotten. But the war transformed it from invention to necessity. It gave the device a new role, the quiet computer of an industrial army. While the West would later celebrate its vacuum tubes and binary codes, the Soviet engineers would look back on this period with pride. For them, computation had not been digital or mechanical. It had been elemental, a struggle of gravity, pressure, and flow. When the war finally ended, and the engineers of every nation compared notes, they realized something profound. They had all been trying to make nature calculate. Some used electrons, some used gears, but in the Soviet Union they had made water think. In the years before and during the war, the Water Integrator evolved from a single experiment into a family of machines. each one more sophisticated, more modular, and more ambitious than the last. Lukyanov began to think not like a mathematician, but like a systems engineer. He imagined computation as architecture, pipes and valves replacing logic gates, tanks as memory, pressure as the invisible thread connecting every part of the system. By 1941, he had drafted the first modular blueprints for a general-purpose hydraulic computer. Each module represented a mathematical operator: addition, subtraction, integration, differentiation. Modules could be joined in sequence or parallel, linked by water pipes to form an analogue of any differential equation the engineer wished to explore. These machines didn't calculate in the digital sense. They modelled. They behaved like the system they represented. And because they were physical, they produced real outcomes. The rise of a water column was a temperature change, the fall of a level was energy loss, the oscillation of a surface was a shock wave reflecting through air. Every inch of tubing mattered. Each restriction corresponded to a coefficient in the governing equation. Each joint carried physical meaning. To change a parameter, the engineer reached not for a keyboard, but a wrench. To observers, it looked like plumbing. But to the men and women trained in differential equations, it was a visual symphony of mathematics. When Lukyanov presented his design to the Soviet Academy of Sciences, they recognized its potential instantly. It was the perfect tool for a planned economy, a machine that could simulate not just buildings, but entire systems: dams, canals, power stations, pipelines. The Academy authorized full production of Lukyanov's hydraulic integrators, each one built by hand in state workshops. The machines were huge: steel frames, hundreds of glass tubes, reservoirs, and gauges. To operate one required patience and precision. The water had to be clean and free of bubbles. Temperature had to remain constant. Every valve had to be tuned by hand. But the payoff was immense. Once calibrated, a single run could solve problems that would take teams of mathematicians weeks to complete. At the heart of the system lay a principle that would later echo through electronic computers: feedback. Water flowed through loops that re-entered earlier chambers, creating self-correcting circuits. These feedback paths stabilized the system, preventing runaway oscillations, a fluid analogue of what electronic engineers would later call negative feedback. To measure results, operators used floats and pointer gauges, tracing the water levels onto graph paper through glass walls. Each reading was recorded by hand, building up the final picture: curves of heat, pressure, and flow. When the output looked right, when the levels balanced and the flows reached equilibrium, the engineers said simply, "The system has converged." It was an early example of a concept modern scientists would call analog convergence: the idea that a physical system, if correctly configured, will naturally settle into the solution of the equations that describe it. The beauty of Lukyanov's design lay not only in its mathematics, but in its metaphor. In a time of scarcity, when the Soviet Union had little access to advanced electronics, this was a computer made from the materials of ordinary life: water tanks instead of capacitors, gravity instead of voltage, valves instead of relays. It captured the Soviet spirit of the era: improvisation, resilience, and the belief that understanding could emerge from the simplest of tools. Later models expanded the concept further. By the late 1940s, Lukyanov's team produced the IGL series, integrator of the Lukyanov hydraulic type, a modular system that could be reconfigured like a construction set. Each module had standard connectors, allowing multiple machines to be joined into vast computational assemblies. Some installations filled entire laboratories. One 1950s photograph shows a young engineer standing before a wall of glass and steel, water shimmering under the lights, valves ticking like a heartbeat. The caption reads simply, "Lukyanov's integrator at work." The Water Integrator soon became a teaching tool. At the Moscow Engineering Physics Institute, students learned differential equations not by chalk and symbol, but by watching water move. To them, mathematics was no longer abstract. It was something they could see and touch. They learned that every physical system could be described by relationships between flows and pressures, the same relationships that governed economics, population dynamics, and energy grids. And so, the Water Integrator trained a generation of engineers to think in systems, not in parts. That thinking would later influence the Soviet cybernetics movement, the push to understand feedback, control, and computation across every domain. What Lukyanov had built was more than a computer. It was a new way of reasoning, one where nature itself became both teacher and student. He once wrote, "Mathematics is only a language, but the world speaks in flows." In that single sentence lay the philosophy of the Water Integrator, and the reason it endured long after the war ended. While Soviet engineers made water think, the West made metal calculate. The race to turn equations into motion produced a generation of analog computers that transformed the practice of war. In Britain, Vannevar Bush's differential analyzer inspired teams at Cambridge and the Royal Navy to build mechanical giants of their own. Each machine was a cathedral of gears and shafts, 6 tons of rotating integrators and precision bearings. At MIT, Bush's machine could solve a 6th-order differential equation mechanically by rotating metal discs against friction wheels, translating equations into geometry. By 1939, these mechanical analyzers had been adapted for war. Britain's Ministry of Supply used them to compute bomb trajectories and aerodynamic curves for the Spitfire's elliptical wing. In America, engineers at Bell Labs and MIT used similar machines to develop ballistic tables and naval fire control systems. Where Lukyanov saw water as a medium of calculation, Bush and his colleagues saw motion. If you could let one wheel turn another in the right proportion, the machine would draw the answer automatically. Mechanical integrators became the West's first true computers, continuous, reliable, and massive. The most famous descendant was the US Navy's Mark I fire control computer, a metallic brain that aimed guns automatically while ships rolled in the Pacific swell. Inside its steel case spun hundreds of gears and rotating ball integrators. The Mark I could calculate shell trajectory, wind correction, target motion, and gun elevation in real time, all without electric circuits. For the men who operated it, the Mark I was a miracle of mechanical logic. Turn a handle, watch the dials align, fire the guns. To naval commanders, it was the difference between guessing and knowing. The ship had acquired a brain. The Germans followed the same path. Their Feuerleitrechner, or fire direction computers, combined mechanical calculators with hydraulic servos that moved gun mounts automatically. Each battery of 88mm guns had its own analog nerve system. Data from rangefinders entered through dials, angles and timings computed by cams, and orders sent back to the guns as pressurized oil pushed pistons. It was an age when every scientist was half engineer and every engineer half philosopher. They weren't just building machines, they were building representations of reality. For the Soviets, cut off from Western electromechanical imports and short of precision metal, the Water Integrator was their equivalent solution. Where the Americans turned gears, Lukyanov opened valves. Where Bush used shafts, Lukyanov used pipes. Each medium, metal or water, carried the same idea: let physics compute physics. By the mid-1940s, this convergence defined a new discipline: analog engineering. Across the world, engineers realized that mechanics, electricity, and hydraulics were simply different dialects of the same language. Flow was flow, whether it moved through wires, pipes, or shafts. In London's Admiralty Research Laboratory, hydraulic servo tables drove gun mounts with astonishing accuracy. In Peenemünde, German rocket scientists used fluid pressure systems to test the V-2's aerodynamics. In Moscow and Kazan, Soviet scientists ran water integrators overnight to model the cooling of turbine blades and concrete walls. Each nation, unknown to the others, was pursuing the same dream: to build a machine that could understand the world faster than the human mind. In 1945, as the war ended, the diversity of analog machines was astonishing. Britain had its differential analyzers, America its gun computers and bomb sights, Germany its hydraulic-electric hybrids, and the Soviet Union its water brains. All shared the same DNA, a belief that the world could be expressed as interacting flows of energy, and that belief was about to give birth to the modern computer. To watch a water computer at work was to watch mathematics in motion. Each glass chamber of the water integrator represented a physical variable. A rise in level signified an increase in value, a fall, a loss of energy. Connecting pipes carried the relationships between them. When water flowed through an orifice, it imposed a resistance R, the hydraulic equivalent of electrical resistance. The greater the opening, the faster the response. At the top of the system sat an elevated reservoir, the power supply. Gravity provided the potential. Below, tanks were linked by precision valves calibrated in millimeters. Each valve was labelled not in litres per minute, but in the constants of the equation, K1, K2, K3. Open the main gate, and the network came alive. Water surged through the pipes, pressure equalizing until the levels settled into their final pattern, the solution. It was an analog integration process, the fluid world performing calculus in real time. Engineers spoke of these machines as living things. A well-tuned integrator breathed. Levels oscillated briefly, then calmed. A poorly tuned one shuddered or choked. What they were seeing were feedback phenomena, the same dynamics that, decades later, would govern electronic control theory. How one equation became plumbing. Suppose an engineer wished to solve the two-dimensional heat equation, partial squared T over partial x squared plus partial squared T over partial y squared equals partial T over partial T times 1 over alpha. Each derivative could be represented as a change in flow between tanks. Temperature T became water height. Thermal conductivity corresponded to pipe diameter. Time to the rate of inflow. By adjusting the valves, one could model steel, concrete, or air. Once configured, the system was left to run. The gradual leveling of water heights was the diffusion of heat. When equilibrium arrived, the final levels gave a full temperature map. A photograph or a grid of readings could then be compared directly with real experiments. This ability to see equations behave made the water integrator a revelation for Soviet engineers accustomed to hand-drawn approximations. The logic of feedback A, looped pipe, feeding one tank back into another, created proportional control. Too much inflow raised pressure, which pushed back against the source. Too little, and gravity increased the draw. The result was a stable equilibrium. Hydraulic negative feedback long before cybernetics had a name. In later models, adjustable feedback channels let the machine explore oscillations, damping, and resonance. Physicists used them to mimic structural vibration, economists later to model price stability. Water, it turned out, could imitate almost anything that flowed. Precision through simplicity. Because every equation was built from real components, errors could be measured physically. A dirty valve caused hysteresis. Temperature changes altered viscosity. Engineers recorded these shifts meticulously, creating calibration charts to compensate. The practice foreshadowed modern numerical correction factors in digital simulation. Despite its primitive appearance, a well-maintained water integrator achieved 1 to 2% accuracy, sufficient for engineering design and often superior to manual calculation. Each run was quick, minutes for diffusion problems, hours for multi-layer systems. For the resource-starved Soviet Union of the 1940s, this was a supercomputer built from plumbing. The operator's craft operating the integrator required intuition. Before a run, the engineer checked that every junction was air-free. Even a single bubble could distort results. Temperature was recorded, valves numbered, initial levels set with a glass pipette. Once flow began, readings were taken at fixed intervals. Ink marks on vertical scales, annotated in notebooks, later turned into graphs. When the final measurements matched expectation, the operator signed the logbook. Solution obtained. These ledgers survive in archives, their pages yellowed but legible, columns of valve settings, pressures, and times. They are, in essence, the printouts of a hydraulic computer. From principle to philosophy, Lukyanov's insight that physical systems could mirror mathematical laws foreshadowed the entire field of analog computation. Every later machine, from the op-amp differential analyzer to modern finite element solvers, owes something to this way of thinking. In the West, analog engineers translated his language into electronics. In the East, his followers refined the language of water. Both paths led toward the same destination, the idea that computation is not bound to a medium, but to relationships. By the end of the 1940s, the Water Integrator had evolved beyond its wartime origins. It had become a national instrument, used in hydrology, geology, and metallurgy, but it still bore the quiet memory of the war that had forged it, a machine of flow born from a world in flames. How? When the war ended, most nations dismantled their analog machines. They had served their purpose. The United States shifted to electronics, Britain to vacuum tubes. But in the Soviet Union, the Water Integrator continued to flow. Through the late 1940s and 1950s, new models appeared under the designation IGL, Integrator of the Lukyanov type. They were standardized, mass-produced in research institutes, and exported to Eastern Europe and China. Soviet planners used them to model groundwater seepage, dam stress, and the cooling of reactor walls. Each calculation began the same way: a technician filling reservoirs, adjusting valves, setting boundary conditions. Water still stood in for mathematics. Gravity still provided the power supply. Hydraulic intelligence. By now, Lukyanov was a national figure. He received the Order of Lenin for the development of hydraulic methods of computation. Yet he continued to describe himself simply as an engineer. When asked why he never adopted electronics, he replied, "Water has no shortages, and it never burns out." In Cold War secrecy, laboratories from Novosibirsk to Tashkent relied on these silent machines. In missile research, integrators modeled heat transfer in rocket nozzles and airflow over fins. In civil defense, they simulated blast overpressure on shelter walls, a grim echo of their wartime origin. Longevity of design. The last operational water integrators ran until the 1980s. In a world of microchips, they looked like relics, yet they remained useful where computers were scarce or power unreliable. Their robustness was legendary: no transistors, no circuits, just patience and a clean water supply. Two complete systems survive today in the Moscow Polytechnic Museum, their glass tanks polished, valves labeled in Cyrillic. Visitors often mistake them for art installations, transparent sculptures of motion frozen in time. But they are more than that. They are the missing link between mechanical calculation and digital computation. A parallel legacy. While the Soviet Union maintained its hydraulic tradition, Western engineers followed a different current. The 1950s saw the rise of operational amplifiers and electronic differential analyzers. In the United States, the Bell Labs Model 5 and the Electronic Associates 120 introduced plug-board flexibility similar to Lukyanov's modular pipes. Both worlds converged again, unknowingly repeating the same principle in different materials. The Iron Curtain divided ideologies, but not ideas. Analog computation on both sides of the Cold War shared a secret lineage of valves, resistors, and feedback. Endurance beyond utility. By the time digital computers arrived, the engineers who had tended the water integrators for decades treated the new machines with quiet skepticism. Digital logic was abstract, invisible. Hydraulic analogues were tangible and trustworthy. You could see an error. You could hear it hiss. One Soviet operator summed it up perfectly in 1975. A transistor never leaks, but you never know when it lies. Water never lies. In the West, while Lukyanov's engineers perfected the art of water computation, another current of hydraulic intelligence began to flow, one driven not by war but by economics. In 1949, a New Zealand-born engineer named Bill Phillips built the MONIAC, a hydraulic analog computer that modelled the entire economy of the United Kingdom using water. Transparent tanks represented households, businesses and government. Coloured dye stood in for money, and flows between tanks mimicked taxation, investment and consumption. When a valve was opened, liquidity quite literally flowed. The result was an eerily living portrait of economic behaviour. Keynesian theory as plumbing. It astonished economists at the London School of Economics. For the first time, they could watch the economy move. When taxes rose, the household tank drained. When exports increased, the investment tank overflowed. The MONIAC was a direct descendant of Lukyanov's idea, a hydraulic integrator reimagined for peacetime. This wasn't coincidence. Phillips had studied engineering during the war, serving as a Royal Air Force officer. Captured in Java and held as a prisoner of war, he built makeshift radios from salvaged parts, a man born to improvise systems. After the war, he saw in water the same power Lukyanov had, an instinct for flow as logic. The British press called it the world's strangest computer. American universities ordered their own MONIACs. A few survive today, water still circulating under museum lights. For Phillips, the lesson was simple. Physical analogies reveal what equations conceal. He'd built the financial world's first liquid brain. Meanwhile, in laboratories from Massachusetts to Munich, engineers were conducting their own experiments with fluid logic. At Bell Labs, fluidic amplifiers replaced vacuum tubes in environments too hot or too radioactive for electronics. At MIT's Lincoln Laboratory, aerodynamicists used shallow water tanks to simulate airflow over jet wings, translating pressure waves into ripples and reflections. In each of these projects, water, air or oil played the same role, an obedient medium that carried mathematics in motion. The boundary between mechanical, electrical and hydraulic began to dissolve. A British engineer summed it up in 1953. The medium does not matter. Only the relationships do. That line might have been Lukyanov's creed, translated into English. Hydraulics to cybernetics. In the 1950s, Soviet scientists such as A. Lyapunov and Sergei Sobolev began to formalize feedback and control theory, the field Norbert Wiener had named cybernetics. Their work drew on both electronic and hydraulic traditions. The Water Integrator had already shown that feedback could stabilize systems long before electronic amplifiers proved it mathematically. Soviet cyberneticians credited Lukyanov as a pioneer, though in Western histories he rarely appeared. In Russian texts, he was the father of hydraulic computation. Where Western engineers saw analog computing as a bridge to digital, Soviet scientists viewed it as a parallel tradition, a living proof that nature could compute without abstraction. To them, Lukyanov's work was not a curiosity. It was a philosophy, computation as embodiment. End of the hydraulic world. By the 1960s, as digital circuits grew cheaper, the analog age began to fade. The MONIACs were dismantled. Lukyanov's integrators went into storage. The great differential analyzers rusted in university basements. But the mindset endured. The conviction that you could learn more from a system by building it than by describing it. Water, air, light, and electricity had each served as analogues of thought. When the digital revolution came, it did not erase that legacy. It built upon it. Lukyanov had once written, "Water never forgets." In a sense, he was right. The equations his machines solved now run silently in the algorithms of modern simulations, their heritage hidden but intact. World War II had left behind another legacy of flow, the science of shock. In laboratories from Berlin to Los Alamos, engineers sought to understand how pressure waves traveled through air, soil, and metal. The mathematics of blast physics was a nightmare, non-linear, transient, and unstable. It defied the simple tables of ballistics. Before digital computation, the only way to see such phenomena was to build them in miniature. Enter the hydraulic analogy once more: shock and water. The same equations that described supersonic gas flows could, under certain assumptions, describe shallow water waves. A rise in surface height was equivalent to a rise in pressure. Wave velocity matched Mach number. Reflections mimicked shock reflections. Scientists filled long rectangular tanks, hydraulic shock simulators. With water, used paddles to generate waves and filmed the results with high-speed cameras. What they saw astonished them. The hydraulic shocks behaved exactly like real blast fronts. In this way, water became a safe laboratory for violence. Engineers studied reflection, diffraction, and the formation of Mach stems, the branching patterns of shock interaction, all through a medium anyone could touch, the analog connection. This research fed directly into hydraulic computation. The same principles that allowed waves to mimic shocks also let integrators solve diffusion and potential problems. The fluid brain and the fluid blast lab were two sides of the same method, using the laws of one domain to predict another. At the U.S. Naval Ordnance Laboratory, similar techniques were used to model underwater explosions, the oscillation of cavitation bubbles, and the behavior of ship hulls under impact. Across the Iron Curtain, Soviet scientists studied the same problems with hydraulic analogues, sometimes using Lukyanov's machines to compute pressure fields from the filmed experiments. From blast to computation, these experiments helped create a generation of engineers fluent in both physics and computation. When digital computers finally arrived, they already thought in terms of analogies and feedback. The code was new, but the thinking was old. The flow of data still mirrored the flow of water. The crossover between hydraulic labs and computer labs was so strong that in the 1950s, Soviet engineers referred to programming as channel design and variable storage as reservoirs. Even language carried the memory of the water brain. By the early 1960s, the world had entered the nuclear age. The same mathematics that once described water levels in glass tanks now governed simulations of thermonuclear blasts. The heritage was direct, though few remembered its source. Every equation for diffusion, pressure, and temperature had once been tested by water. Lukyanov's integrator, built for peace and reconstruction, had unknowingly trained the generation that designed the Cold War's most destructive devices. It was an irony history would never quite acknowledge, the gentle flow of water helping humanity model the violence of fire. In every war story, there are names that fade into the footnotes. Vladimir Sergeyevich Lukyanov should have been a household name, the man who made water compute, yet his work remained almost unknown outside the Soviet Union. Partly this was secrecy, partly modesty. He never sought personal fame, and Soviet publications of the 1940s and 1950s rarely credited individual inventors. When Western journalists asked about the liquid computer in the 1960s, official responses called it simply a device for solving engineering equations. but inside the USSR, Lukyanov was regarded with quiet reverence. His students called him the engineer who made nature speak mathematics. The builders behind the brain. The Water Integrator was never a mass-produced machine like a tank or radio. Each one was hand-built, unique in scale and configuration. Dozens of technicians, glassblowers, welders and instrument fitters assembled the chambers by hand. They were craftsmen of computation, though few ever knew the word. Archives mention two senior collaborators, A.N. Lebedev and E.A. Rudakov, both specialists in heat transfer. They adapted the integrator for civil engineering problems, then later for the study of materials under stress. Each model they produced was an experiment in itself. Their notebooks are filled with sketches of pipes, joints and tank arrays, handwritten parameters beside pencil-drawn graphs. To them, a successful computation was not a row of digits, but a picture of equilibrium. A working community. The workshops that produced Lukyanov's machines were quiet places, the opposite of the roaring Soviet factories around them. In these rooms, engineers listened to the hiss of valves and the whisper of running water. They recorded pressures with ink pens and marked time with stopwatches. When an experiment finished, they drained the system, polished the glass, and began again. To outsiders, it looked archaic. To those who worked there, it was a kind of music. Old colleagues recalled that Lukyanov was patient, almost ascetic. He believed machines reflected their makers, that a careless hand produced noisy results, but a calm hand made water flow smoothly. In this sense, the Water Integrator was not just an instrument, it was a mirror of discipline. Recognition at last. In 1951, the Soviet government awarded Lukyanov the Stalin Prize, one of the country's highest honors for scientific achievement. His citation read, "For the creation of an instrument for the solution of complex differential equations in the fields of thermodynamics and engineering." It was cautious wording, but the award was substantial, recognition that the machine had saved years of labor and helped the country rebuild after the war. Yet, in the West, few ever heard of him. His papers were published only in Russian, behind political barriers that kept scientific communities apart. When analog computing became fashionable in the 1950s, names like Vannevar Bush and Lord Kelvin filled textbooks. Lukyanov's did not. Only after the Cold War's end did researchers rediscover his work, preserved in the archives of the Polytechnic Museum and the Russian Academy of Sciences. By then, he had been gone for decades, his invention almost forgotten. While Lukyanov's water integrators solved physical equations, another revolution was brewing, one made of electrons and switches. In 1945, the same year Soviet engineers ran their first large-scale hydraulic models, the United States unveiled ENIAC, the world's first fully electronic digital computer. It filled an entire hall with vacuum tubes, consumed enough power to heat a building, and performed 5,000 additions per second, a miracle by contemporary standards. The age of discrete calculation had arrived. Where Lukyanov's machines embodied equations, ENIAC encoded them. The digital computer was not an imitation of physics, it was an abstraction. Numbers became symbols. Logic became voltage. For most of the world, this shift marked progress, from continuous flow to binary control. But for those who had grown up in the analog age, something was lost. The intimacy between operator and system disappeared. No longer could one see the solution forming in the rise of a water level or the spin of a gear. Computation had become invisible. Two philosophies, analog engineers believed in representation, the idea that any system could be represented by another system obeying the same laws. Digital engineers believed in translation, that everything could be converted into code. The difference was cultural as much as technical. In the West, efficiency and miniaturization favored binary logic. In the Soviet Union, where resources were scarce but ingenuity abundant, Analog methods persisted because they could be built from almost nothing. Yet both sides pursued the same dream: to make prediction certain, to make complexity controllable. Whether through valves or vacuum tubes, they sought mastery over nature's equations. The long merging. By the 1960s, the two traditions began to merge. Electronic analog computers adopted modular patch panels that mimicked Lukyanov's reconfigurable networks. Digital scientists studying feedback borrowed directly from analog control theory. In this synthesis lay the future of computation: hybrid systems blending continuous and discrete models. The modern concept of simulation, letting software mimic the real world, was born from this union. When a computer today models fluid flow, it is performing digitally what Lukyanov's integrator did physically. The difference is speed, the principle is identical. A world transformed. The digital tide could not be stopped. Within a decade, analog computers were museum pieces, yet their influence persisted in every engineering code, every simulation, every system model. In this quiet continuity, Lukyanov's legacy lived on. Every digital simulation of heat or pressure carries within it the same logic: divide the problem, connect the parts, let them balance until equilibrium is reached. It is the water integrator in binary disguise. The medium changed, the mathematics did not. By the 1970s, the world had entered the Silicon Age. Digital computers shrank from rooms to desks. The rhythm of computation changed from the murmur of pumps to the pulse of transistors. Analog computing, once the crown jewel of engineering, became the language of a fading generation. The water integrator still stood in Soviet laboratories, its gauges polished, its tanks refilled each morning, but fewer and fewer students came to learn its operation. To the new computer scientists, it was a relic, elegant but obsolete. Yet even in decline, it possessed a quiet dignity, endurance through necessity. In rural research stations across the Soviet Union, electricity was unreliable. There, digital computers could not survive, so the analog machines continued, driven by gravity and patience. In a flood control institute near Novosibirsk, engineers still used hydraulic analogs to predict river overflow each spring. At a mining school in the Urals, a single Lukyanov unit calculated ground subsidence until 1985, nearly 50 years after its invention. Maintenance was ritual. Each morning, technicians checked every valve, removed air bubbles, and recorded water temperature. A slip of 2 degrees could alter results by a measurable margin. It was slow, deliberate work, computation at the pace of nature. Analog persistence in the West. Even as digital systems rose, the West too preserved a few analog strongholds. NASA's Flight Research Center used mechanical integrators for real-time simulation of aircraft controls until the mid-1970s. The US Navy maintained analog fire control trainers because their continuous response better matched real physics. At universities, analog labs persisted as teaching tools, letting students see differential equations as motion and voltage. The principle survived not out of nostalgia, but because it remained uniquely intuitive. Digital logic could predict outcomes. Analog logic could explain them. The culture of touch engineers who had grown up with analog computation often described it as craft. They spoke of tuning rather than programming, listening rather than debugging. The language itself revealed a tactile intimacy now lost. When they retired, they left behind notebooks filled with valve settings, calibration charts and sketches, an art form disguised as mathematics. In those pages, history whispers, the feel of a lever, the sound of a pump, the shimmer of an answer forming in glass. By the 1980s, the last Soviet water computers fell silent. The laboratories that housed them were converted to offices, their tanks drained. A few were stored in basements, others dismantled for parts. But two, perhaps by accident, perhaps by care, were spared. They became museum pieces, not because they had failed, but because they had succeeded too quietly to be noticed. Today, in a quiet corner of Moscow's Polytechnic Museum, the last surviving water integrators stand behind glass. Visitors pass them without a glance, mistaking them for industrial art, a lattice of pipes, gauges, and reservoirs. Few read the small plaque, Hydraulic Integrator of V.S. Lukyanov, 1936. If you listen closely, you can almost hear the echo of water, the heartbeat of computation long before silicon. One machine sits disassembled, its pipes open like the veins of a fossil. The other, restored in 2011, can still operate. Curators occasionally fill its tanks for demonstration. Coloured water flows through transparent channels, rising and falling in slow, hypnotic rhythm. It solves no modern equation, yet it still obeys the laws it was built upon. When the levels stabilize, a visitor sees what Soviet engineers saw 80 years ago, a thought made liquid, from relic to revelation. In the museum's dim light, the water integrator looks alien beside modern computers. There are no screens, no switches, only flow. Yet every concept familiar to digital engineers is present: input, output, feedback, integration, error correction. It is the same logic in a different form. Scholars who study the machine today call it the missing chapter of computing history. For decades, textbooks began with Charles Babbage and ended with Alan Turing, ignoring the engineers who solved equations through motion, temperature, and pressure. But as historians rediscover these devices, a more complex picture emerges, one in which analog and digital, East and West, coexisted rather than replaced each other. Symbol of an era. To the older generation of Russian scientists, the water integrator represents more than a technical achievement. It is a symbol of a time when computation was a craft, when a solution was something you could watch unfold. It reminds them that the world's greatest problems, the stresses in steel, the heat in concrete, the pressure in blast waves, were once tamed not by code, but by patience. In that patience lay a kind of wisdom, the understanding that every system, if given time and balance, finds its own answer. That was Lukyanov's philosophy, and perhaps the secret of his success. In the 21st century, engineers still talk about flow, but now they mean data. Rivers of information, channels of transmission, feedback loops of control. The metaphors remain hydraulic because the logic never changed. Every modern simulation of fluid dynamics, every finite element solver for heat or pressure descends in spirit from Lukyanov's machine. The equations are the same, only the medium has evolved. Supercomputers now model turbulence that no integrator could contain. Yet deep inside their code, the same patterns reappear: integration, convergence, equilibrium, all ideas first realized not in mathematics, but in water. The echo of analog: when a scientist sets boundary conditions in a digital model, they are doing what Lukyanov did with valves. When they run a solver to equilibrium, they are letting the system converge as his tanks once did. When they visualize results as color gradients across a grid, they are seeing the modern mirror of water levels in glass. The world changed medium, but not meaning. The return of the liquid brain. In laboratories today, researchers build microfluidic computers, chips where water or oil droplets carry logic through channels etched in silicon. The principle is identical to the 1936 water integrator, but miniaturized to the microscopic. Nature's oldest computer has returned, reborn in technology 1,000,000 times smaller. In the same way, scientists studying neural networks often describe information as flow, signals balancing across connections until a solution emerges. Once again, the idea of equilibrium rules. The machine remembers water even when it runs on electrons. Final reflection. The water integrator began as an engineer's curiosity, became a nation's secret weapon, and ended as a museum relic. But its spirit endures. It proved that intelligence can emerge from matter itself, that understanding need not be abstract, that the world can compute its own laws if we only give it the chance. Lukyanov did not build a computer to replace thought. He built one to reveal it, to make the invisible visible, to let mathematics flow. The next time we watch a computer simulate a storm, or a spacecraft's re-entry, or the spread of heat through metal, we are watching the descendant of a quiet Soviet machine that once solved the unthinkable, not with electricity or code, but with the simplest force on Earth, water seeking balance.